Imagine trying to prove something exists that you can never see, never touch, and never directly measure. That's been the challenge with dark matter. We know it's there, galaxies wouldn't hold together without it. But every experiment designed to detect it has failed, until now. NASA's Fermi Gamma-ray Space Telescope has detected a halo of extremely energetic photons around the Milky Way's center that matches predictions made decades ago. The pattern is so precise, so unexpected, that even the scientist who discovered it says this would mark the first time humanity has seen dark matter. Professor Tomonori Totani from the University of Tokyo published his findings on November 25, 2025 in the Journal of Cosmology and Astroparticle Physics. Within 48 hours, the scientific community was buzzing. What he found? Gamma rays with exactly 20 gigaelectronvolts of energy, that's 20 billion electron volts, forming a halo structure around the galactic center. Here's the key: the shape, the intensity, the energy spectrum, everything matches predictions made decades ago for what we should see if dark matter particles collide and annihilate each other. Not approximately, not kind of similar. It matches with a precision that's frankly unsettling. If confirmed, this is one of the most important discoveries in physics this century, because for 95 years we've been hunting for dark matter. We know it exists, we just couldn't see it directly. But why did it take 95 years? Here's what makes this discovery so significant. Dark matter was first proposed in 1933 by Swiss astronomer Fritz Zwicky. He observed the Coma Cluster over 1,000 galaxies and found they were moving far too fast. Their visible mass provided only 1/6 of the gravity needed to hold them together. They should have scattered into space billions of years ago. Zwicky's solution: invisible matter, providing extra gravitational pull. He called it dunkle materie. His colleagues thought he was wrong. Then in the 1970s, Vera Rubin proved Zwicky right. She measured stars at the edges of galaxies moving just as fast as stars near the center. Impossible unless massive invisible halos surround every galaxy. By the 2000s, the evidence was overwhelming. Dark matter makes up 85% of all matter in the universe. Everything you can see, every star, planet, galaxy, represents only 15%. The rest is invisible. But here's the problem: we still couldn't detect it directly. So why couldn't we find it? It's not for lack of trying. Scientists have built detectors deep underground, kilometers below the surface, trying to catch dark matter particles passing through Earth. Experiments like Lux Zeppelin, Xenon, buried in abandoned mines. Billions of dollars invested. Results? Nothing. The Large Hadron Collider tried to create dark matter particles by smashing protons together at near light speed, the most powerful particle accelerator ever built. Results? Nothing. Space telescopes searched for dark matter signatures in galaxy collisions, in cosmic ray detections, in X-ray emissions. Decades of work, thousands of scientists, nothing confirmed, until Professor Totani looked at 17 years of data from NASA's Fermi telescope in a new way, and he found something that shouldn't be there: a glow at the center of our galaxy, gamma rays with a very specific energy, in a very specific pattern. What exactly did he find?
The leading theory for dark matter: weakly interacting massive particles, WIMPs. Hypothetical particles with mass that create gravity but don't interact with light. They pass through normal matter almost like ghosts. Almost.
Theory predicts if WIMPs occasionally collide, they annihilate in a burst of energy, producing gamma rays with a specific signature, and that's exactly what decades of physics calculations said we should look for. Totani focused on the galactic center, where dark matter should be most concentrated. And there it was, gamma rays at 20 gigaelectronvolts, distributed in exactly the halo pattern predicted by computer simulations. The intensity corresponds to WIMP particles about 500 times the mass of a proton. Other gamma ray sources don't match this pattern. Radioactive decay, wrong energy; supernova remnants, wrong distribution; pulsars, wrong intensity profile. Totani's analysis shows conventional astrophysical sources cannot easily explain these observations. This is either dark matter or something completely unexpected that happens to look exactly like dark matter. But can we trust this? Now, and this is important, we need to talk about skepticism, because we've heard dark matter detection claims before. They didn't hold up. Dr. Sean Tulin, a theoretical physicist at York University, told Live Science he wants independent analysis, and he's right to be cautious. Science requires verification, not just discovery. But here's why this is different. Totani is using 17 years of Fermi data, far more than previous studies, and crucially, he himself emphasizes caution in the paper. He explicitly states independent confirmation is essential. the signal must be verified in other dark matter-rich objects by other teams using different analysis methods. This is responsible science, a remarkable claim published in a peer-reviewed journal with clear statements about what's needed for confirmation. No premature victory laps, just solid analysis and a call for verification. So what happens now? Over the next 6 to 12 months, other research groups will download the public Fermi data and run their own independent analyses. They'll check for systematic errors, test alternative explanations, see if the signal holds up under scrutiny. Scientists will also look for similar gamma-ray signatures in dwarf spheroidal galaxies, small galaxies dominated by dark matter. They'll examine galaxy clusters where dark matter is highly concentrated. If multiple independent observations confirm the same pattern across different objects, the case becomes exponentially stronger.
And if this is confirmed as dark matter, the implications are staggering. We'd finally know what 85% of the universe's matter actually is. We'd confirm that WIMPs exist, opening up entirely new physics beyond the standard model. We'd validate decades of theoretical predictions and computer simulations.
But more profound than any of that, we'd have direct observational evidence of the invisible foundation that shaped the entire universe. Think about what dark matter actually means. After the Big Bang, the universe was almost, but not quite, uniform. Tiny density fluctuations, barely perceptible variations in matter distribution. Without dark matter, those fluctuations would have stayed tiny. The universe would have remained a thin, nearly uniform soup of hydrogen and helium, slowly cooling, forever dark. But dark matter amplified those fluctuations. Its gravity pulled gas together, created the first structures, allowed the first stars to ignite, built the galaxies, created the cosmic web, the large-scale structure of everything. Dark matter isn't just an abstract physics puzzle, it's the reason we're here. Without it, no galaxies, no stars, no planets, no life. It's the invisible scaffolding upon which everything visible is built. And we may have just glimpsed it for the first time. After 95 years of searching, after billions spent, after thousands of scientists dedicating their careers to the hunt. Right now, as you watch this, dark matter particles may be passing through you, trillions every second, barely interacting, and 26,000 light-years away at the galactic center, they may be colliding, annihilating, producing the gamma-ray glow Totani detected, a signal that's been there all along, waiting for us to see it. Write in the comments, do you think this is really dark matter, or will it turn out to be something else? And if confirmed, what should the next generation of dark matter experiments look for? Subscribe if you want updates as this story develops. Thanks for watching. Until next time.